Hello students, let us continue our discussion on current electricity, and today I am going to take a new concept which is EMF and internal resistance of a cell. Okay. So, this word EMF seems to be new for you and internal resistance of a cell. Okay. So, now you have clarity about different types of cells. I think you have studied the different types of cells, dry cell, electrolytic cell and other cells in chemistry. I am not going deep into the cell and its constituents, but I will be making use of electrolytic cell in order to understand the factor EMF of a cell. Okay. So, here EMF stands for electromotive force. Okay. Yeah, we'll get to know what and all are they, don't need to worry about them. You just follow this. Assume you have an electrolytic solution, okay, or we call that as electrolyte, right. So, this is the electrolyte filled in a container, okay, and you have two electrodes immersed into it. Okay, these are the two electrodes immersed into the electrolyte, and these two are connected to an electrical device. Okay, the general electrical device that we consider normally is a resistor, and this is how a simple battery, a simple cell, electrolytic cell look like. All of this together makes an electrolytic cell. And now these two electrodes which we have immersed, one of that is a positive one and the other one is a negative electrode. Okay. This positive electrode will have certain potential V plus with respect to the electrolyte. Okay. So, this V plus is the potential of this electrode, the positive electrode with respect to the electrolyte. Okay. So, which means the potential difference between this electrode and the electrolyte is V plus, okay, and the electrolyte. Now, coming to this negative, let V minus or minus V minus, okay, be the potential difference between the negative electrode and the electrolyte. Okay, electrolyte is the solution of the cell, electrolytic cell, you know that, right? And this electrolyte will have constant potential, okay, throughout it, but these electrodes immersed, okay, will have their own potentials. So, this positive electrode will have V plus volt of potential difference with respect to the electrolyte. Okay, this rod and this electrolyte, the potential difference is V plus. Clear? Similarly, here the electrolyte and the negative electrode will have the potential difference of minus V minus. Okay. So, this is about the basics of a cell. Okay, this is how an electrolytic cell looks like. And as long as the circuit is open, okay, as long as the circuit is open or not closed, there will be no current in the entire circuit, which means there will be no flow of charge from this positive to negative electrode or between the electrodes. There will be no flow of charges, which means that itself is no current, we say. Okay. And outside the cell, okay, so this is the electrolytic cell. Outside the cell, as we know, the current always flow from positive terminal of the battery to the negative terminal of the battery. Okay, that is how outside this, that is how the current flow outside the cell. But when you come to the inside of the cell, the current flows from negative terminal to positive terminal of the battery, okay, or the cell. So, this is how the charges move. Okay. Yeah, I am considering the flow of positive charge. Assumption is the positive charge is flowing, and hence we are getting current. I'll also explain the practical situation of free electron flow. For now, see, now the current flows from this positive charge, positive terminal to negative terminal outside the cell, and inside the cell the current actually flows from negative to positive. That is when the circuit is complete, isn't it? The current flows through this electrolytic solution from negative to positive through chemical reactions, and hence outside the current will be flowing from positive to negative, and hence the current continuously flow like this. Okay. So, this is the basic idea of cell and the flow of current inside the cell. Now, this potential difference between the electrolyte and the electrodes, okay, which is V plus and V minus, this potential differences together, okay, will have certain ability, okay, because whenever you want to move a certain charge, or whenever you want to get certain current in the circuit, you need to have a potential difference, isn't it? Without potential difference, you cannot get any current in the circuit. Okay, this is the external part of the circuit. You cannot have current until and unless you have potential difference between these two electrodes. And now the potential difference between this electrode, the positive electrode and the negative electrode itself is taken as the EMF of the given cell. Okay, here it is V plus minus of V minus. So, this is E, we normally make use of E itself. Okay, you will also find the symbol like this, but this is not epsilon, something similar to E itself. You can take E, that is always preferred, and we also make use of small letter e to represent EMF. These are the symbols used to represent EMF itself. Okay. So, now this E, the electromotive force E, is given by V plus V minus. So, this much of potential difference between the electrodes is responsible for the current that we are getting in the circuit. Okay. So, now this we already knew, this itself is potential difference of the cell, isn't it? See, when you have a cell, this is the representation of a cell, the circuit symbol. So, this is always positive terminal, this is always negative terminal. The potential difference between them was already taken as V volts in various other examples or derivations, isn't it? We took V volt as the potential difference, and the same potential difference is maintained across any electrical device connected like this. This we already did, but why the new symbol E? This V itself now is taken as E. Okay. What is the difference between that V, the actual potential difference, which we call that as terminal potential difference, okay, TPD, and this E, electromotive force, EMF? See, it is somewhat like this. You can assume this battery, okay, either this or this, has certain ability. Okay, so you can think of like a bike. Okay, whenever they give this a particular bike is capable of giving say 60 kilometer mileage. Okay, which means per liter it gives 60 kilometer mileage. So, that is what is somewhat like EMF of that bike, which means it is capable of giving 60 kilometer at standard conditions. Okay, it is not yet tested in the real road, in the practical situations. Okay, now you come to practical situations. You go across, you will face different conditions of the road. Somewhere the road is not proper, somewhere the road is muddy, and somewhere the road has positive slopes, I mean the slopes and all. There in those kind of situations, and you will also face traffic jams. So, all those are the practical situations. So, when you actually come to the practical situations, the mileage of the bike drops to 45 to 50, isn't it? That is what actually happens. But the seller has told you that this bike is capable of giving you 60 kilometer mileage, isn't it? So that is the similarity of EMF and the standard mileage of the bike. Okay, so when they give you the battery, a cell, it is mentioned on the cell. This cell is 1.5 volt capable one. Okay, that the whatever they mention on the cell. Okay, you take a dry cell, they always mention +1. It's 1.5 volt, 3 volt, 9 volt cell, 9 volt battery and all. What is that? 1.5, 3, 9 and all. They are the potential difference between the electrodes. Okay, this value EMF. Okay, that itself is the EMF. 1.5 volt is the EMF of a particular cell. Okay, you can see it on any cell that you take. Now the question is, then what is that difference between EMF and the voltage, actual voltage? Okay, EMF does not depend on any device that you connect to the battery. Okay, you take a battery, EMF of that battery is fixed. Okay, it is fixed after manufacturing. EMF is fixed, but when you take the terminal potential difference, okay, which we in short we call that as TPD, terminal potential difference. This is the actual potential difference between the electrodes. Okay, that itself V, the terminal potential difference, is also the potential difference, but that TPD, terminal potential difference, depends on what kind of electrical device is connected to this cell. Okay, so that is, this TPD is similar to the actual mileage given by the bike. Clear on that? So the practical situation, whether you are connecting a high resistance or low resistance, that decides V. Okay, the terminal potential difference. Whatever you connect here, that does not decide E, the EMF of the cell. EMF of the cell is fixed, which is somewhat like the efficiency, the mileage of the engine given by the seller. Now the new, when it comes to practical situations, what kind of electrical device that you connect, similar to on what kind of road you drive the bike. Okay, you choose very good road, mileage will be very good. You choose a bad road, the mileage will be bad, it will get lesser. The bike will give lower mileage. Similarly, you give you connect some electrical device here with less resistance, and hence you can expect more current, isn't it? And hence the terminal potential difference will be varying. Okay, so terminal potential difference, okay, which we represent as V, which we normally represent as V, and this is what we always been taking. This V itself is what we always have been taking when it comes to the derivations. We have derived the combination of resistors, isn't it? Resistors in series, resistors in parallel, and even the combination of capacitors. There and all, we took this cell connected to the devices, electrical devices, with V volts across this cell, isn't it? So that V is terminal potential difference, not the EMF of the cell. Okay, so now let me define EMF. I hope you have the conceptual clarity. So EMF, the electromotive force. Okay, EMF, the electromotive force. Okay, this can be taken as the property of a cell, inherent property of the cell. Okay, that is fixed. You take certain cell, EMF is fixed, 1.5 volt, 1.45 volt fixed, but you connect the same battery to a particular device. Now you measure the potential difference. There it is not 1.5, it will be lesser than 1.5, because you have connected to some external source that will reduce the ability of the cell. Okay, clear on that? So now EMF can be defined as the, see, this is potential difference itself. EMF is the potential difference itself between between the electrodes of the electrolyte, isn't it? Nothing else. The potential difference between the electrodes of a cell right? A positive electrode and a negative electrode. The potential difference between the electrodes of a cell when the circuit is open. What do you mean by open circuit? Open circuit means there is no current withdrawn or taken from the cell, okay, which means the cell is not in use. The cell is not connected to any of the electrical devices. It is left as it is, okay. That is what open circuit means. You have disconnected, you just disconnect this part, so that the total circuit is disconnected, okay. There is no current drawn. It is very similar to simply a cell kept at certain place without connecting it to any other electrical device, okay. So this is the potential difference. EMF is the potential difference, okay. So since this is potential difference itself, why this force term coming here? Because EMF means electromotive force. Why the word force comes here? Because this is because of certain historical reasons. In previous days, when the current electricity was in the beginning stage, scientists assumed that this cell is providing certain force to the charges to flow, isn't it? Even that is what even we think of when we say when there is some motion happening or when there is certain acceleration happening, we always think that okay, someone is applying the force, isn't it? And similarly here, the scientists thought that the charges are pushed by the battery using this force, electromotive force, okay. But the actual reason is, it is the potential difference between the terminals of the battery which is responsible for the motion of the charges, isn't it? That we now know that. But historically, when the concept was not that evolved, they assumed that there is a force given by the cell to the charges for their motion through the electrical device, and hence they named it as electromotive force, okay, the force responsible for motion of electrons, okay. So don't need to worry about all those things. They are all historical reasons. I just gave you the conceptual clarity. So basically, EMF can be defined as the potential difference between the electrodes of a cell when the circuit is open, okay, or when the cell is connected in open circuit. This is fine. Now the symbol is E, okay, and the definition of TPD, terminal potential difference, is given by, again, the potential difference between the electrodes, of a cell, the same definition, okay. Once again we are measuring, okay, the potential difference between the terminals of the cell or between the electrodes of the cell, nothing else. But this time the circuit is connected to an external electrical device like a resistor or a capacitor, whatever, okay. So whenever you have some electrical device connected to this battery, which means when the circuit is closed, then you measure the voltage across the cell, the potential difference across the cell, and that itself is our TPD, terminal potential difference. See, they are the same. The potential difference between the electrodes of a cell when the circuit is closed, okay. So this is about the definition of EMF and TPD. Now when and as I said, EMF is represented by E and the TPD is represented by V. Now when we connect or when we close the circuit, now is there current in the circuit? Yes, there is current in the circuit. Now everything is connected. The electrons will start to flow from this terminal to this terminal, or let me take the current itself. The current starts to flow from since the circuit is closed, the current starts to flow from positive electrode through the resistor of certain resistance R into this negative electrode like this, and inside the current flows from this negative electrode to this positive electrode, and the current I, rate of flow of charge, is same at all the points. You take here, 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 here. This is very similar to a series connection, isn't it? Everything is continuous, there is no splitting of circuit. So the current is same throughout the circuit, which means whatever the current that we are getting outside the circuit or outside the battery of the circuit, the same current shall be seen inside the battery. Okay, the same current is what is flowing like this, going like this. So the same current I will be flowing through the electrolyte, isn't it? This is the electrolyte. You take dry cell, the composition is different. Since I cannot, it's difficult to represent it in dry cell, I have taken the example of electrolytic cell. The same concept can be extended to dry cell. Okay. Now this electrolytic solution will offer certain resistance to the flow of this current, isn't it? The very nature of any material is offering resistance. Okay. Yes, there are certain materials at certain temperature where they can offer very less resistance, very less resistance. But when it comes to the practical situations, every material, every metal, whatever you take will have its own resistance. It may be small, but it will be there. Okay. With the same approach, we can see here that this current flowing through the electrolytic solution will experience certain resistance to the flow inside the electrolyte, okay, due to the electrolyte, I can say. So that resistance by the electrolytic solution or by the electrolyte of the cell for the flow of current is called internal resistance of the cell, isn't it? Because see, this is the whatever the resistance that we have connected here is the external part, okay, but this internal resistance is the internal property of the cell. Okay, this property is decided when the cell is manufactured. Okay, so there is one more important term here, which is internal resistance. Internal resistance is represented by small r. Okay, the regular external resistance is represented by capital R, and this internal resistance of a cell. Okay, whenever I say internal resistance, this is a term associated with a cell. Okay, EMF and internal resistance are the terms associated with a cell. These are the properties of the cell when it is, even when it is not connected to any other device. Okay, so these are the properties which they acquire or gain when they are manufactured. Okay, they are decided. Now internal resistance of the cell is defined as, again, resistance means the opposition for the flow of current. By what? By the electrolyte of the cell. Okay, so internal resistance of a cell is defined as the opposition offered for the flow of current by the electrolyte, of a cell. Okay, so this is defined as internal resistance represented by small r, and this is the definition of it. Very simple. Okay, the opposition offered for the flow of current by the electrolyte of the cell. This electrolyte will offer certain resistance, and that itself is internal resistance of the cell, small r. Okay, and this you can visualize since we have taken electrolytic cell. When you have dry cell, it's little difficult to visualize, but even the material placed between the electrodes of the cell, okay, even in a dry cell, materials placed between the electrodes of a dry cell will also offer certain resistance. Okay, that is the same resistance which is internal resistance of the cell given. And when it comes to practical situations, the internal resistance of a cell will be very less. Okay, the practical applications we are concerned, where we can say that the internal resistance of the cell is very less, and hence we consider that the EMF and TPD are almost the same. Okay, that is what we consider. But when it comes to the theoretical approach, the actual solving problems, solving the problems, when it comes to solving the problems, EMF and TPD are different. Okay. Now, what is the mathematical relation between this E, V and R? There is a mathematical relation between E, V and R. So, as I say, which term should be greater, E or V, EMF or voltage? Again, consider the example of the mileage of the bike. Bike has greater mileage according to the seller, that is what is EMF. So, then the seller will always give the best mileage. So, EMF is always greater than the terminal potential difference, isn't it? So, EMF of a cell is always greater than terminal potential difference of the cell. Now, what is the actual relation? Say you have I ampere current flowing through the circuit, I, okay. Then what happens is E becomes equal to, okay, E becomes equal to, this V will always be there, okay. And where is the other part of the EMF spent into? Okay, you consider the example of the bike itself. So, they said that okay, it is the bike is capable of 60 kilometer mileage, but now you are getting 50 kilometer. Where is the other 10 kilometers going? The other 10 kilometers of mileage, the ability is spent during the brakes, during the when you keep the engines on in a traffic signal. Okay, so they are the places, they are the situations where you have spent the other 10 kilometers. Isn't it? Because that is where you are experiencing resistance for your motion of the bike, isn't it? Even here, the other part of the EMF, okay, V is what it is externally providing, okay, out of this E, V is given to the external electrical device. The other part of E is spent, okay, on the internal resistance or spent in overcoming the internal resistance of the electrolyte. Okay. So, this is what is the ability of the cell, okay, be clear, EMF, and this is what it supplies outside, okay, V, and this is what it spends to overcome the internal resistance of the same cell. Okay. For example, say you have a cell of 10 volt, okay, 10 volt is the cell, but you can see if you have the voltage, the terminal potential difference outside, when you actually measure after connecting it to a resistor, you find that V is 9 volt, but they have rated on the cell that it is 10 volt cell, the EMF is mentioned 10 volt, but you see that when you actually connect it to some bulb and check, it is showing you 9 volt. Okay. So, where is the other 1 volt going? That 1 volt is spent in overcoming the resistance of its internal resistance, okay, overcoming the internal resistance of the same cell. Okay. So, that 1 volt is this IR. Okay. That is how you can connect EMF, TPD and internal resistance mathematically. Now, E is fixed, as I say, the value of E and R are fixed for a given cell when they are manufactured. You can't alter them until you alter the internal structure of the cell. They are fixed once the cell is manufactured, E and R. And V, the terminal potential difference, is then decided by, what are the factors by which V is decided? From the same expression, V becomes equal to E minus IR. Okay. Now you can visualize what is happening here. So, this is what is the output that you get for the electrical device that you connect, right? Terminal potential difference. E, it is fixed, okay, it is fixed when it is manufactured. So, you take better cell of higher EMF, you will get good TPD. Okay, that is one way. The other way, you take a cell with least resistance. Okay, that will also give you better V. Okay, so the best way of getting higher V, the maximum voltage, maximum TPD, is choosing a cell of higher EMF and lesser resistance, higher EMF, lesser resistance, because it is minus. Okay, and the other factor that you have here is I. What is this I? I is the current through the circuit, which is same internally and externally, isn't it? I is same internally and externally. So this I current is decided by what resistor, what amount of resistance that you connect externally, isn't it? More the external resistance, lesser the current that you get in the entire circuit. Following? So this is what is the ability of the cell and all, that's fine. But on what factor does this I depend on? This factor I, the current, you know that very well, depends on the resistance of the resistor that you connect, or resistance of the any electrical device that you connect. I have given you the example during Ohms Law itself, isn't it? More the resistance, lesser the current. You assume the example of pipe filled with marbles or stones or some obstacles. Now you put water, then more the obstacles, lesser the water coming out every second. So the rate of flow of water will be lesser you have if you have more resistance, isn't it? So the external resistance R decides, the external resistance R decides the value of current I in the entire circuit. So when you want more current, you connect an external resistance of of higher resistance value. When you want a lesser current in the circuit, you connect a resistance of lesser resistance externally. Okay, you cannot alter small r; it is fixed. Okay, it is about choosing the cell. Once you have chosen, now you want a better TPD. Then what you do is reduce the current in the circuit. If you reduce the current in the circuit, again V will be higher. Okay, following? So these are the ways of getting better value of V, and this is the mathematical expression for terminal potential difference and EMF with the internal resistance of the cell. Okay, I hope you are clear with all these things. And that's very important formula. They ask it in your board exams, even you will get it in problems. And now we have the final expression for current through the circuit. Now that can be obtained as follows, because the Ohm's law states that the current through the circuit, I is equal to I is proportional to V in such a way that V is equal to IR, isn't it? This is what is Ohm's law, and this V is the terminal potential difference between the terminals of the battery, terminal potential difference, TPD, not EMF. But when they give you the data, they don't give you TPD in problems. Okay, in many problems they will just simply give the voltage, the term TPD, but when it comes to the problems based on cell itself, okay, when you get the problems based on cell itself, they provide you the data in terms of EMF, not TPD. Okay, so we need to get the expression for current when EMF of the cell is given, internal resistance of the cell is given, and the external resistance connected is given. Okay, yeah, you can do that by first getting the value of V and then putting that into IR. Okay, that is also fine, but you can get the direct expression for I as follows. What is V equal to? The TPD equal to IR, right? So from the same expression, IR becomes equal to EMF E minus I into internal resistance of the cell IR, I current into R. Same current will be flowing, okay, externally and internally. Now we need the expression for I. Let me bring this IR here, and hence I will have I of I can take as common factor, and inside the braces I will be left with R plus R, which is equal to E, and hence the current I becomes equal to E by R plus R. Okay. So this is the final expression for the current flowing through the circuit in both internally and externally. Okay, internally means inside the cell, externally means outside the cell. The current will be same. What is that current equal to? I equal to E by R plus R. What is capital R? External resistance connected. What is small r? Internal resistance connected. Okay, internal resistance of the cell, fixed value. E is the EMF of the cell. Now they don't need to give you the value of V TPD. Okay, even if they give just the value of EMF, you can get the current flowing through the circuit using this expression. Okay, yeah, you can get it by using even if you don't have this formula, you could have obtained first. You can take you can obtain V here. Yeah, again you have a problem for that. You have current here, but the expression for current, we don't know the current value. That itself is what we are finding. So yes, this expression is very important. Okay, yes. So this expression is important one when it comes to finding the current through the circuit when you have a cell with considerably good internal resistance, smaller, and capital R is the external resistance connected, and E is the EMF of the cell given. Okay, if they give TPD, you simply go for this, that is enough. Okay, if they give EMF, then you should go for this formula to connect to get the expression for current through the circuit. Clear on that? So that's it. That is about this cell, internal resistance, TPD, EMF, and the relation between all of them.